Okay, in this video we're going to continue our study of the characteristics of functions. We're going to start off with extrema. So extrema involves maxes and mins of a function. So let's start off by breaking it down into two main groups. We've got our locals and our absolute. Our local maximum is the maximum value of a function on some interval, and a local minimum is the minimum value, okay, thinking about our y values, our range values, of a function on some interval. The absolute max or min is the absolute lowest y value for a function for the minimum, or the absolute highest y value for a maximum. Okay, so the notation we're going to use when we state that a point is a max or a min, we're going to call it, make sure we distinguish whether it's absolute or local, whether it's a max or min, of whatever the y value is at whatever the x value is. So let's look at an example. Okay, let's say we're given this graph of a function. We're given the coordinates of the extrema, and we want to state which one's which. So let's start off with this guy up here. So it looks like this function is bounded above. So we've got an absolute max here. Notice that the highest point here, 6, is higher than the other local max. So now an absolute maximum is also a local maximum. It just happens to be the tallest of those. So absolute maximum of 6, our y value, at -7, which is our x value. Okay, go into our minimum. We've got a local minimum here. Now, why is it not the absolute minimum? Because our function keeps going forever and ever in the negative y direction on the two tails. So there's no lowest point since it goes forever down. But on this interval, it is the lowest point, so we call it a local minimum of -4 at x equals -1. And for our other maximum, local, let's see, that should be maximum, let's fix that. Our local maximum of 4 at x equals -3. Okay, another characteristic of functions is the symmetry of a function. A function can have symmetry with respect to the y-axis. Remember, y-axis is the vertical axis. In this example of f of x equals x squared, we've got a parabola opening up. If you take the function on the right side of the y-axis and fold it over the y-axis, it folds over onto itself. So it's symmetric about the y-axis, or with respect to the y-axis. So that's the graphical version. If we look at some data points from that graph, we've got our x's on top, y's on the bottom. Notice that the y values are kind of also symmetric with respect to the extreme, which is that 0, 0 point. Okay, so 1 and -1 both have a range of 1, or a y value of 1. 2 and -2 gives us the same value. So any number that we plug into this function and its opposite will give us the same value out. So that's indicative of an even function, such that anytime we plug in the opposite of an x coordinate, we'll get the same function back out, the same y value. To test this algebraically, if we take our given function, so in this case f of x equals x squared, and if we substitute in -x, so let's do f of -x, plug that into our function. When we square a value, it's the same as multiplying it by itself. So -x times -x is positive x squared. So we get our f of x out. That's a good way to check algebraically that we've got an even function. Okay, another form of symmetry is with respect to the x-axis. So in this example, we've got x equals y squared. We've got a parabola opening to the right. Notice that if you took the top half of this function, folded it over the bottom, it would line up, it would fold over onto itself. So symmetric over the x-axis. Here's our table. We've got our x values on top that come from our y values in this case. Okay, and notice that if we tried to do our function test, our vertical line test, it would fail. So this is not a function. Anything with anything symmetric with respect to the x-axis is not a function, since it has to have at least 2 y values. We can say there mirrors any coordinate x, negative y, has another coordinate on that function x, positive y. Okay, our last one, symmetric with respect to the origin. Our example here, f of x equals x cubed. We've got our graphical representation. Graphically, symmetry with respect to the origin, if you fold it over the x-axis and then over the y-axis, it'll overlap on itself. Here's our data table. Notice that we've got the same 7 points as in our first example. Notice that the y values, the first half are negative until it gets to our 0, 0, and the rest are positive. So the same absolute value, but first half are negative. So this is a type of an odd function. Odd functions, algebraically, if you plug in the opposite of x, then you're going to get the opposite of the original function out. So if we plug in f of negative x for x cubed, then we get negative x times negative x times negative x. 3 negatives make also a negative, so we get the opposite of x cubed, which is the opposite of our original. Okay, good way to check to see if a function is odd. Okay, so let's do an example of kind of combining all of the characteristics, all of the ways to analyze a function into one problem. So in this problem, we're given f of x equals x minus 4 over x squared minus 7x plus 12. And we want to find these characteristics: the domain, the range, the asymptote, points of discontinuity, if it's increasing, decreasing over any intervals, any extremes, and then the symmetry of that function. So all these we're going to find for this one function. First thing I would do is I would graph it. Put it in your graphing calculator or plot a bunch of points. In this case, I've given a little sketch of it up here. So it's a rational function, so we should expect a couple pieces maybe. So this is what we got here from our graphing calculator. So I'm going to start with the domain. Remember to find the domain. We've got a denominator here, so we want to take our denominator, set it not equal to 0. We solve that equation or inequality, and we find that x can't be 4, x can't be 3. So on our function at x equals 4 and x equals 3, it's undefined. So for all other points, it is defined. So interval notation, we've got from negative infinity to 3,
Attention staff and
from
students,
3 to
at
4,
this time,
and then from 4 to
we are
positive
releasing
infinity.
the downstairs
The
room
range.
to go to lunch.
To find the range,
At this time,
let's look
hold
at
everyone
our
else
graph
and all downstairs rooms and the gym, both modular
and our
buildings.
asymptotes.
will be released
So maybe
for
let's look at our
lunch.
asymptotes
I
first.
will announce for upstairs
From our
in a few
limit
minutes.
worksheet, our asymptotes, we can find our horizontal asymptote from our table. Notice that the power of the leading term in the denominator is 1 bigger, so it's greater than the top polynomial. So we're going to have a horizontal asymptote on our x-axis, y equals 0. And for our vertical asymptote, we've got x equals 3. Okay, range is going to be defined from this point, negative infinity, all the way up to our horizontal asymptote, which is at y equals 0. It picks up on the other side of 0 and goes all the way up to this hole here. So it stops at 1 and then goes all the way up to positive infinity. Okay, so let's talk about that hole. On your graphing calculator, it's not going to show you that hole, but after we factored out the denominator, And we saw that we have x minus 4 on the bottom as well as on top, and that shows us we've got a hole at x equals 4. Okay, plugging that in to what's left, which would be 1 over x minus 3, and that gives us our hole is at 4, 1. So hole at x equals 4, which is a removable type of discontinuity, and we've got infinite discontinuity at our vertical asymptote, x equals 3, this infinite gap here. Okay, it's never increasing, so from left to right, our function is always decreasing, and the interval for that, since our function is always decreasing, is the same as our domain. There are no extremes, no maxes or mins. We've talked about asymptotes. Find the symmetry. Let's check for even or odd symmetry. So we want to find f of negative x. So everywhere you see an x variable in our function, plug in negative x and simplify. So simplifying that all out, we get neither f of x or negative f of x. So f of x is neither even nor odd.